put yourself in the queue. Can you hear me? Not loud enough? Okay.
Okay, it's 1:30 a.m. in California and time to start. Welcome everyone to Yokohama IETF 116 first routing working group meeting, and we'll guide you to your update. Not well, if you are participating in IETF process, you agree of all the rules. Please do read it. There's common IETF policy that one has to disclose intellectual property, as explained in RFC 8179. Specifically to routing working group, will require you to state whether you are aware or not of particular APR that might pertain to work you are doing, or work you are reading, or work you are hearing about. We do it before working group adoption. We do it before last call. And unless every author and counter has responded, work is not going to progress. We haven't adopted new working group documents. Existing working group documents, good work going on. The RIB extent pending AD review. BGP peak, a lot of going back and forward. AD reviews are to be addressed. The AD has sent draft back to working group and asking for updated version. ATN BGP ongoing work is really large document, and we're also waiting for progress on 6man. TI LFA draft, the comments have been addressed. So we would like to thank Stuart and Alex or Sasha for the review, and we will start working group last call after this IETF. We are getting an update on QoS Young model and plan to start the process after this IETF as well. So there's number of drafts again. Please review what's going on, what we are doing here. There's some new work as well. Agenda for Friday, we'll review it Friday, and we've got new wiki. Please review the wiki. We are going to publish all the stuff that's going on in working group on the wiki. And as compared to old one, it's actually easy to use, readable, and please do use it. And we are ready with the presenter.
Hey, I'm in
The
the
first
queue.
presenter, right?
We have AC in the queue. AC, go ahead.
AC Lindum, champion of inclusion language. What's going on with the VRP Viz document?
Which one? Can you say it again?
Yeah, the VRP update with all-inclusive language.
PIP 50 something, 5598 or something like that. Let me see it.
So I believe we should start preparation for progress, and
yeah, I got some
comments about the document, mostly positive, right?
I got some good directorate reviews and some good comments. Yeah, so
yeah,
I
think
50.
for that. Sorry.
Go ahead.
I think for that draft, after the directory reviews, I see the document is pretty much ready. Then we can start the working group last call. We'll find a shepherd for that document.
Okay, great. Thanks.
I missed it in the working groups, this working group update, but I do have it in the RTG wiki. Yeah. So in the RTGWG wiki, if you are looking for a status for a specific working group document, you can always find information there. If it's old or you think it needs to be updated, just let the chairs know.
And going forward, we are planning to put all the update there, so you don't need to search through mails and what's not. Okay?
Okay.
So we are ready for the presentation.
Hello. So, hello everyone. My name is Asim Chaudhary, and I will provide update on QSN model. So, essentially, next slide, please. So, as part of this version of the model, we are able to take care of all the young doctor comments. We have added some of the acronyms and definitions. We have language modifications, as well as we have simplified the naming conventions, and we have make sure that some of the names are actually matching to the RFCs. Also, we have in this version of the draft added a QS design diagram in which we have shown that we have a couple of base modules, which is traffic policy module as well as QS section module. And on the top of that, we have derived policy modules, which are like DivSer policy module. Also, we have queuing policy module as well as scheduling policy module. So essentially what DivSer policy module and all these policy modules do is take the base template from the traffic policy module as well as action from the QS section module and combine the different match criteria with the actions and come up with their own policy module. And so that is how it become a DivSer policy based on those match and actions, or it will become a queuing policy based on a queuing related action and matches. Similarly for the scheduling policy. Okay, and in addition to that, we have added a queuing configuration example, which I explain in the next couple of slides. Besides that, we have also added INA consideration section, and based on that, we have come up with the next version of the model. Next slide. So in the queuing policy configuration example, if you look, we have created 3 classes of traffic, voice, video, and data. And voice, video, data is essentially based on a standard DSCP match criteria as typically used in the industry. Like the voice will be explicit forwarding, so on and so forth. And we are using these classes of traffic into the in defining the queuing policy. Next. Okay. So if we look into the queuing policy definition, we have 3, in this example, we have 3 classes, the voice, video, and data, and we have added few actions to it. So if we look into the various actions for the queuing policy, we have a priority definition, and if the priority value is less, that actually indicates the priority of the class is much higher, is higher. So for example, a priority level of 1 is actually higher priority than priority level 2. In addition to priority, we have defined a minimum guaranteed bandwidth, which is defined by min rate. And similarly, we have defined maximum shaping bandwidth defined by the max rate. So if we, I have not included these actions for the video and data, but essentially these are similar kind of actions. So if we look into this particular example, we have a minimum guaranteed bandwidth of 20% for the voice. Assume that we have 20% for video and data as well. That takes up the 60% of the bandwidth of the link. Now we have remaining 40% of the bandwidth. Now if you look into the shaping rate, which is 30%, so essentially we, so the voice traffic being a higher priority will take extra 10% of the bandwidth, making it 30% complete. If the traffic of the voice is exceeding 30%, it will be capped at 30%. Now remaining, so we have 20 plus 20 plus 30, which becomes 70%. So rest of the 30% of the bandwidth will be divided equally among video and data, assuming that the priority for video and data are same, which is say priority level 2. If video has higher priority than data, then it will have higher precedence over the data. Otherwise, if they have the same priority, then the bandwidth will be, remaining bandwidth will be shared equally between the two. Next slide. So as a next steps, essentially we had taken care of all the young doctor comments. We probably will be adding maybe one more example for example, the scheduling policy. Scheduling policy will essentially take a queuing policy at the leaf level and create a hierarchy of QS policies. And this scheduling policy then apply to an interface. So we'll probably take one such example to clarify further how the scheduling and queuing policies are related and how these are applied to a particular interface as a target. In addition to that, essentially we'll look into any more changes which might be required. We'll essentially review our draft further to make sure that we are not missing anything. And similarly, we'll try to improve any further description for various parameters which we had defined as part of the model. Once these simple steps are over, we'll go for the last call again. Okay. Yeah, sure. Thank you.
I'm Changwan Lin from Nutrition Technology. I'm going to talk about consideration for protection of SR networks. Next slide, please. Protection of SR networks could be divided into path protection and egress protection. In actual deployment, path protection could be further divided into local protection and end-to-end protection. Local protection is performed by the node on the forwarding path. TIFA could be used for local repair. Also, BFD detecting interface or the direct neighbors could be used for lewness check of local protection. End-to-end protection is performed in the ingress node. SR policy hot standby could be used for end-to-end protection. When all paths of SR policy failed, the BE path could be used for protection of SR policy TE path. Also, BFD detecting for the SR policy status could be used for lewness check of end-to-end path protection. When egress node failed, the path protection does not work. So the packet should be forwarded to another egress node of same service. That is egress protection. For egress protection, the pending node is performed local repair, and the egress node perform the service fast rerouting. Also, BFD for the egress node seed or IP address for the liveness check of egress protection. Next slide, please. Pass protection and egress protection could be used at the same SR networks. For example, from P1 to C2, there are 4 paths, and the prime path is P1, T path from P1 to P2. And there are 3 backup paths. The backup path 1 is B path from P1 to P2. And the second backup path is B path from P1 to P3. And the third backup T path is from P1 to P3. When the prime path failed, the egress node should select best backup next hop by the local policy. The local policy, egress node first policy, the B path from P1 to P2 could be preferred. By T first policy, the T path from P1 to P3 could be preferred. Next one, please. Next slide. The state of running code, hardware device and software implementation, which has been passed SRv6 protection interoperability test hosted by China Mobile in the past 2 years. Also, both the single AS domain and the inter AS domain have passed the interoperability testing. The trials of SRv6 protection in 5 branch networks of China Mobile in 2021 and 2022. Next slide, please. The implementation or recommendation of SRB deployments. The egress node enabled service fast rerouting and also enabled BFD for the seed or IP address of the egress P node. All nodes enabled TFA for local repair, and BFD enabled for link and delete neighbors. Next slide, please. The SRT deployment. The egress node enabled service FHAR, and also ingress node enabled SR policy hot standby. Also, ingress node enabled SRB path backup for SRT path. Ingress node enabled BFD for detecting the SR policy state. Also, ingress node enabled BFD for seed or IP address of egress node to detect the liveness of egress node. All nodes enable TFA for local protection and enable the BFD for delete links and neighbors. Next slide, please. The changes of this draft. After IETF 113, we replaced the draft new RTGWG SRv6 protection consideration 02. Both MPOs, SR and SRv6 are included. Next slide, please. Next, any questions and comments are welcome. We are seeking for adoption call. Thank you.
So we've got Greg in queue, but before we go with him, question to you really. So what you're describing here is well covered in different documents that pertain to both SR and SRv6. the framework is well understood, right? The difference between local to path protection to not to link protection. So what's your plan with the document? Just to describe all the techniques all together, describe implementation of particular part of the world, a particular vendor. How would you like to progress it?
We want to seeking for adoption call.
But this draft right now is informational. It's a summary of existing technologies that's been developed for segment routing. Right? You are not proposing anything new.
We out IETF 130, we include MPLs as the first version. We just about SRv6 protection.
Oh, okay. Oh, you want to help?
Yeah, but
Yeah, I'm a co-author of the draft. Wei Changcheng from China Mobile. Yes, I think this draft is just to give some information how we deploy the protection, and all those solutions in this draft have been discussed in IETF, maybe other draft. So this is an informational draft. Yeah.
Okay,
Greg. Yeah.
Thank you. Greg Mirsky, Ericsson. Can we roll a couple, like 2-3 slides back? If possible. Yeah, that's what we'll do. So I really wonder, so what you say, you have so many BFD sessions, and what you expect that BFD for locator will be, or prefix SID, because we need to remember that BFD does not tell us what is going on a box that is hosting this locator seed. So we really only verify the forwarding path and forwarding engine to a certain degree. So we are not really verifying their state or condition of this entity that hosted on this box. So really, because what it seems like that might be, especially since if this is SR and PLS, then using LSP ping with a proper target FAC will be more appropriate, because that will give you verification of correlation between data plane and control plane. So just something to think about, because it's not really clear what the purpose of using BFD session and so many. Thank you.
From egress node, the BFD could be set long parameters, and
again, BFD, what it looks like, many of your BFD sessions will follow the same path. So I really see it's overcomplicating and duplicating and complicating OEM. Because what will happen if you have a network failure, that you will have multiplicity of alarms that will basically be caused by one event. Okay, because if we look at your diagram, so at least I see that blue, red, and green are crossing the same path effectively. Okay, so 3 BFD session for the same path, it seems like overreach. Again, how you characterize the purpose of your session, to me, it looks like what you're verifying correlation, consistency between the data plane and control plane. So you're really verifying that this particular seed being programmed and you can reach it through this data plane. And that's the purpose of LSP ping in MPLS network.
Yeah, thank you, Greg. I think it's a good suggestion. But at this moment, in order to deploy those protection easier, now we really use the BFT session for each pass. But as you just mentioned, we can optimize that. Thank you.
So since the document is informational, it would be really good if you could actually have some consideration actions. How many BFD sessions are you using? How do you make sure that local BFD does interact with end-to-end BFD? And as Greg rightly say, in some cases you verify reachability. In some cases you are trying to verify actually the egress seat that can provide potentially more than just reachability. Right, so it would be very useful if you put consideration section. And again, you're describing the particular deployments. Probably you've considered different technologies. It would be really good for the readers to understand as to why you ended up using particular set of technologies, particular timers, and so forth. And perhaps Greg could help with some OM details.
Yeah. So I think here we give a full picture of the how the protection solution in for the different services, but it's not necessary for one operator deploy all those solutions. Depends on what service you need support. So it's a little bit complicated for this page, but in fact, maybe you can use the different solutions in different application scenarios. Yeah, we will double check Greg and hope we can optimize those solutions, especially for OEM. And but I think this document is mature enough, so we would like to ask for adoption. Yeah.
I think we can continue the discussion on the list. Yeah.
Okay, thank you.
Thank you.
Thank you.
Hi, hello everyone. My name is Han, and I'm going to talk about some new scenario for the multi-region SD-WAN and some protocol extension that is needed for the overlay routing. Next slide, please. First, let's talk about why we need the multi-region SD-WAN. As we all know, the SD-WAN is used to connect the headquarters and the branches between the enterprise, and some VCP is deployed in the cloud, so it's used to connect the enterprise to the cloud. But for some big enterprise, the headquarters may locate in one country and the branch located in another country. Sometimes they are even located in different continents. So if we only use one hop to connect between the CPE, we can only rely on the public internet to do so. But the public internet quality can be not good. So to solve that problem, we need to deploy this middle mile SD-WAN POP gateway to establish this kind of multi-hop tunnel to improve the connection quality between edges. So basically, this POP, the connection between the POP can be the locally the basin link. So you can connect multiple locally basin link to provide a better connection than the global public internet. Next slide, please. And to do so, effectively, we are extending the SD-WAN from one hop to multi-hop. And if we are doing so, there may exist multiple overlay paths between the CPEs. For example, as you can see in this picture, the blue one and the yellow one are two different overlay paths, but they all reach from CPU1 to the CPU3, and we are facing the choice to choose the best one. By best, we kind of mean the shortest in terms of latency. So to solve this problem, we need to do the overlay multi-hop routing. And the background of this SD1 is that based on this IDR working group document, we only have the BGP as a control plane of the SD1, so we don't have IGP. So we need to extend the BGP SPF for the overlay topology. And each SD1 node, by node I mean the SD1 edge, like this CPE, and the middle mile gateway, like the POP in this picture. And they also need they need to advertise the overlay topology, the link adjacency to each other, and they need to synchronize. After that, each node can run the overlay SPF algorithm to calculate the best effort route. Next slide, please. And we can go one step further. That not only do overlay best effort, we can do the overlay TE. The requirement is that we have different terminals may go through the different underlay, and their quality is different. And for SD1, you need different application have various SLA requirement. For example, the video conferencing may need high bandwidth, and the voice traffic is sensitive to the latency. So how to match the how to match various SLA requirement of the application to the underlay link is a problem. So we can use the overlay TE to solve that problem. As you can see from this picture, for example, the voice traffic from CPU1 to CPU2 have some tight latency constraints, so it cannot go from the above link. The POP is 100 milliseconds. So we need to choose some shorter latency link between these CPE. In order to do that, we need to connect the terminal, the SLA information of each terminal. For example, the bandwidth and the latency and the packet loss. Remember, this is also this is the overlay terminal, so it's not the underlay link. And after that, the controller can connect the SLA of each terminal, and it can calculate the terminal list satisfying the SLA requirement of the application. Basically, it can specify a list of terminal, and it can send that terminal list to the edge, and the edge can specify can carry the terminal list on the data plane. So that the POP can forward to find the right path. Yeah, next slide, please. And finally, we have a requirement of the SD1 multicast. As we all know, the multicast traffic is very common in SD1, especially in the enterprise. You need to distribute some traffic from the headquarters to the branch. As you can see from this image, it's very typical multicast traffic. And SD1 is overlay. The underlay may support multicast, but the SD1 is not aware of it, or in many cases, the underlay is the internet link, so it does not support multicast. So we need to do the SD1 multicast on top of the multicast-free underlay. To do that, basically we have two options. We can move the underlay multicast technology on the overlay. The first option is that we can do the PIM over SD1, but as we all know, the PIM is slow to converge, and we have a new multicast technology called BEER, we can do the beer over SE1. And but beer requires the IGP. Since we only have BGP, so we need to extend the BGP to carry the beer topology information. So we would like to prefer the option 2 that requires to extend the BGP. Next slide, please. Yeah, this is the summary. So we identify that we think that a multi-region SE1 is a key solution for the enterprise WAN network, especially in this cloud network area. And doing so, we identify several necessary enhancements for the routing protocol listed above. And when we submit, after we submit the draft, we receive some comments that the draft is not very clear about what is new comparing to existing SE1. I hope this presentation can make it more clear, and we will update the draft this week. Any questions and comments are welcome. Thank you.
I've got a couple of comments before we go. So number one, you could use BGP for multicast signaling. We've been doing this for years. Complexity of introduction beer is non-trivial, and it's not supported by all silicons require change to data plane. So you might still be looking into something that would support simpler implementation. And again, BGP, there's a variety of BGP implementation for multicast signaling. And same question as to previous presenter. What you've described is pretty much vanilla SD1 has been on the market for the last 10 years, right? I'm looking forward to your proposals with regards to routing protocol enhancement. So far, you're just describing what's been there, what's working, and what's really known. So where would you like to go with the draft?
This draft is a requirement draft, and if we can find more people interested in this one, we can also propose more solution based on this requirement. Does this answer your question?
Yeah, so I would really like you to ask on the list whether people are interested. Again, by looking at it, it looks like, when reading the draft, it looks like SD1 solution has been in the market for forever, for the last 10 years, right? So please do talk to mailing list, to working group, and see whether there's enough interest to just describe what there is. And people are willing to spend time and effort to describe it. Tony?
Okay.
Tony P. Juniper. Just saying the IDR, so BGP extensions for beer have been going for quite a while. The stuff is very far. I think we're like towards last call. So if you need extensions, more SD1 extensions into this work, then please go look up at the draft and change whatever you need. Thanks.
Okay.
Thank you.
Thanks.
Okay. Okay, thanks. So the next two presentation will be about signaling in networking, in network computing operations. This is draft we present in IETF116 in London. My name is David Lu. Of course, this draft is co-authored with my colleagues, Jin Zhe, Luigi, Cui Ming, and others. Next slide, please. So what we have done since IETF115, follow the advice from the chairs and ADs, we split this draft into two parts. So the first part is the main spec, which covers the rational use case, and the framework and the protocol itself, the header itself. Basically, it defines the data operation. So what do you need to do with the data, or what happens to that data? but it does not say where to do it and how to do it. So the second document about deployment consideration covers actually the aspect of where in the network it should happen and how it should happen. So everything related to the network routing or other aspects are covered by the second document. Another update is we added the new author, Jing Zhe, is also my colleague. Yeah, next please. So if you look at the main spec, the updates, so the relevant use case and the in-network generic operation stays the same. And we put some updates on the framework. So from our perspective, there will be a framework for the in-network computing in general, followed by a newly added chapter called data operation mode. It's trying to illustrate two different modes. One is individual mode, the other one is a batch mode. So individual mode refers to the data operation can be happens on one single source. So for instance, if you want to generate a log for a one source or generate a sequence number, it's independent of other sources, while batch computing modes is something like you have to collect several inputs from different sources in order to perform the next step. For instance, the aggregation of the data from different sources, right? Then the thing header get updated. I will illustrate into detail in the next slides what has been updated, followed by a newly added chapter about the requirements on the control plane. Although the control plane design itself is not in the scope of this document, but we anyway want to add a kind of requirement statement for the control plane. Next, please. So a bit recap. I don't know what happened on the wording, but a bit of recap on the use case. Signaling in network computing actually helps a lot. So we list the three different use cases: net reduce, net lock, and net sequencer. So from experimental results, we can see that by leveraging the in-network computing capability, it can dramatically improve the overall performance if you ask the switcher or routers in network to perform some data operation. So for instance, in the net reduce, apparently asking switch to do the aggregation of the data improves, makes the system runs 1.5 times faster, and the system will scale much better. In terms of, for instance, a net lock case, we see that the network device can generate a lock nearly 10 times faster than a lock server can do, right? So all in all, shows that the in-network computing can help a lot with certain use cases. Yet we need a explicit and general mechanism to tell the switch or router in the network what to do and how to do. Please, next. So this is actually overall framework. You will see that it consists of hosts from both ends, host A and host B, right, on screen. Then we have a ingress and egress proxy, which is responsible for the encapsulation or decapsulation of the packets. And the ingress is also responsible for routing the packet to the right node who has that capability. So that's actually its overall requirement from the control plane, right? Control plane will tell the ingress proxy actually which node has that capability, so the ingress node can do that accordingly, which will be depicted into detail in the deployment consideration draft. And then, of course, there's need for a sync capable switch or router which is able to execute all the data operation for the application. So here, we want to emphasize that the host should be sync aware, which means the host knows our host defines what to do with the data, what should happen with the data. But the host is not necessary to be aware how the network will treat it and where will be treated. Next, please. So in the sync header, while largely kept the same, but we add one more flag called down flag. 0 indicates that the request has not yet be performed, while 1 means has been done. Why to do so? Because in some case, might be due to the overload of the switch, might due to the late arrival of the packets, whatever reason, the operation might not be done, right? In that case, it's not really affordable for a switch to wait for forever. So for that reason, we set a flag, down flag, indicates whether the operation has been done or not. Because if not done yet, then it's up to the server, the other host, to perform that, or throw it away and depend on the requirements of application. But in the network, we need to indicate. Next, please. Some requirements for the control plane. Actually, the control plane in general should be aware about switch resources, right? He should be aware which switch or router in the network is capable of doing what kind of operation, whether he's fully loaded or still have capacity. So this can be achieved by periodically pulling or kind of querying those devices. The control plane should be able to select the switch routers based on certain constraints, should be able to define the paths so that he can inform or configure the ingress nodes to perform the right routing, right? And of course, the control plane should be able to monitor the failover or monitor the situation and to perform certain activities if there's a failover. Next, please. So this is about the main spec. I guess I can probably continue, and then I will wait for the comments afterwards. Is that okay? Yeah. Okay, yeah. So I will continue with the next presentation about deployment consideration. So as I said, for the main spec defines what to do with the data, while the deployment consideration is more about how the network will treat it. So basically, we inherit the example of sync over SFC from the original documents, but what we add here is the general deployment consideration plus another example, sync over MPLS. Next, please. So some general consideration, because the experiment was done actually in the lab with a simple network topology, while we, in the reality, the network will be much more complicated. So that the sync capable switcher routers should periodically advertise their capabilities and capacities to the network, while the control plane should be able to aware that there could be multiple pulses. So he has to really create a proper route for the packets, for the data in the packets. That will untake the desired computation or data operation, right? The encapsulation or the tunneling can happen either in layer 2, 3, or 4. It's really dependent on the context and application environment. We discussed that internally, and we find that all of the layers are possible. Is really, and also we all find different encapsulation protocols. It's really depend on what is already existing there, and then we can just use that. And last but not least, the header usually copied, not moved, which makes it easy to access. Next, please. So example of sync over SFC. So what happens, for instance, in the host, you will find that the host define the sync header, define where the data comes, how many data, how much data, and what should be happen in the data. And then if we use service function training, and then we will create the NSH header, right? So we copy the sync header to there. Here, there's one small thing I have to correct. It's not 100% a copy because remember in the sync header, there's a field called data offset. So when you copy the header from the hosts to the encapsulation protocol, the data offset has been updated. And then the ingress will do that and then forward the package to the SFF, and then forward to a sync capable node, do the operation. After that, both data and the sync header will be updated. Remember, there's a down flag. That flag might be updated. And then the payload, probably the data will be updated as well. And then in the egress, it will be copied back. And of course, when you copy the back, you have to update the offsets again. Next, please. This is one example. Yeah, a little bit awkward in alignment, but probably you can still see that we try to actually create the NSH encapsulation with the base header first, and then service path header, followed by the sync header. So one thing I need to mention probably in the base header for the MD type things for our sync is just 16 bytes. So we use MD type 1 used here. Of course, if we get updates to find 16 bytes is not enough, we might define a different MD type. The service path header as defined in RFC 8300 and the sync header as defined in the previous slides. Next, please. Similar example happened to MPLS. So we also copy the header here, updates the offsets, the forward to the SLR with the sync capable with the sync capability to do the data operation, and afterwards we copy it back. Next, please. And here is a kind of illustration about how we actually use MPLS to do the encapsulation. So it might be a stack of labels pushed one after another, but it's really defined actually in the MPLS. Yeah. Next. Yeah, that's about it. Encourage the discussion in the list, and yeah, also welcome to contribution. I'm looking forward to question. Adrian, yeah.
Adrian, go ahead.
Hi, Adrian Farrell. I think I'll wear my cat's chair hat here because I want to just tease out the differences between this and CATS, because that may help people understand where to put the effort. I see that this is as an overlay as well, but this is on-path computation between two endpoints where some function needs to happen. So in that sense, it's very similar to service function training. There's a flow that's going from A to B, and before it arrives at B, something has to happen to it. Whereas CATS is talking about A to B, where B is the computation point, and B will return to A the resulted computation. And what CATS is doing is working out which B to use and how to get to it. And you're doing how A and B are fixed, and you're trying to pick a path between them that will achieve the computation. Have I got that?
Right, right. thanks for clarification. It's perfect aligned. Aligned with your statement. So we actually try to define something which will happen in the network. While how it will happen, I give two examples, SFC or MPLS, or could be other GRE or others. Maybe CATS can bring more solution there. While for us, it's mainly focused on defining what happens, and that should happen in the network on 1 point or 2 points.
Lovely, good. I'm a lot more comfortable. I have some technical issues as well about how the transit nodes know that there's a sync header underneath the encapsulation.
Well, basically the transition node, you mean the node just forwarding the packets to next hop?
Yeah.
Well, basically they are not aware about that because you encapsulate that as kind of a payload. While they, for instance, in case of MPLS, you just pop up or just pass by, right? Switch the labels, pass by, but the sync capable one will actually find that there's a header. He can understand that, and
Okay, so the sync capable nodes are deep parsing to find the sync header. I got you.
Yes, thank you.
Adrian, you're done, right? I'm not next in queue. So practically, you're describing collective operations, not really A to B operation. It's a network that's trying to do some functions and distribute information back to everyone who has data to send and process, right? At least this is how NetReduce looks like.
Right.
Right. So the operation is stateful, and you're not really building routes, you're building trees. And you shouldn't do anything to the tree before each node that participates in collective operation gets the data back, which brings a lot of questions about how do you signal when operation starts and ends, resiliency. So collective operation can take really long time for something like large language models, right? So none of these considerations are the drop. This solution doesn't match the problem statement, doesn't match the solution. If you're thinking about collective operations, try to take a look at Sharp, for example, right? So the complexity is really in maintaining the trees, providing coherency and consistency across all participants in the in-network compute trees. So I would expect much more in your document rather than just encapsulations. And again, we are looking at collective tree operation, not really A to B. So it kind of creates the wrong perception, I would think.
Good point. Good point. I want to comment back. Basically, yes, you're right. When we wrote the current draft, maybe have not really tackled those consideration or aspects. We assume that this in-network computing will happen in a closed environment, in a controlled environment, not in the open internet yet, because in that case, you probably cannot really anticipate when the packet will arrive and how long it will be wait. Whatever, we're starting from a limited domain, basically. For instance, in the data center where the environments are more or less is under control, so you know that the packet will arrive more or less in time. But I agree that even in a controlled environment, something might went wrong. So in that case, more things need to be considered. But this is one thing. Especially for the batch computing mode where you need multiple source, right? But if you only do that from one source, maybe it's less complex. So if you only, for instance, generate one lock from to answer the request from one source, this might be simpler. Yeah, but I agree. In general, that's more need to be considered.
We'll continue on the list.
In the queue. Yeah.
Yeah, okay.
David?
Go ahead. Yeah, just be
David
brief.
Lamparter. This goes a little bit in the same direction as the previous comments. I think you need to focus on the characteristics of the computation rather than the computation itself. So whether you have some element in the network that can do a calculation that is on the single packet versus needs an amount of packet. And I saw in your draft that you list actual operations, and I think it's actually better to remove that and cut the scope off. Just describe what different cases you have targeted here, and even maybe think about how the network can signal that it is capable only of this operation that only looks at one packet, maybe. And that also goes to the other comments.
Yeah, I think you're right. So basically, the switcher router with that sync capability should actually announce its own capability, whether it can do this operation or not, whether it can process that in line rate or not, and how much it can do. So that's need to be put into probably separating somewhere else. Yeah. Okay.
Thank you.
Thank you.
Please continue the discussion on the list. And with that, we are adjourned. Thank you everyone for your attention, and we'll see you on Friday.
Thanks, everyone. Enjoy Tokyo and see you on Friday.